Hello, my name is Álvaro Martínez. The talk is about upper and lower bounds for topological indices on unicyclic graphs. And this is a joint work with José Manuel Rodríguez from the Universidad Carlos III de Madrid. So let me start with the definition. A topological index is just a single number, which is computed on the molecular graph and correlates with a molecular property. So as you can see in this graphic, this shows the correlation between the heat of formation in bentonite hydrocarbons and the geometric arithmetic index. And as you can see, it's a very good correlation. So what's the interest of topological indices? Well, the interest is that computing a number in a graph is much easier and cheaper than conducting an experiment. So just by doing some computation, you get a good approximation of the molecular property you are interested in. So there are different approaches to define topological indices. One of the main approaches is based on the degrees of the vertices in the graph. This will be the case of the variable first Zagreb index, which is just the addition of the degrees to some exponent, or the Narumi-Katayama index, which is just the product of the degrees of the vertices. There are many others degree-based topological indices. Also, other approaches as the Wiener index, which is based on the distances between the vertices, which is the addition of them, or other approaches, other ways to define a topological index. In this talk, we are going to focus on degree-based indices, and these two will appear later. So what's the problem we want to address? The problem is we have a unicyclic graph with n vertices. Unicyclic means that it has only one cycle in the vertex. If we take one edge of this cycle, we obtain a graph with no cycles. That would be a tree. So we want to know for this unicyclic graph with n vertices, we want to know which is the best possible upper and lower bound for the value of a few topological indices. And we want to do is either fixing or not the maximum degree. The technique we are using is majorization through Schur-convex functions. This was applied to topological indices successfully by Eliassi and Gavalan, and proves to be a very interesting tool in this subject. So let's start by not fixing the maximum vertex degree. So we have a unicyclic graph with n vertices, and we want to know which is the best upper and lower bound for a few topological indices. And we are going to work as generally as possible, giving a general method, so we can obtain bounds for many different topological indices at the same time. So let's start with Schur-convex functions. So we have two n tuples, two vectors with n numbers, which are ordered in decreasing order. And then x majorizes y if this partial addition of the first k elements is greater or equal than the partial addition of these first k elements for every k, and the total addition is the same. So in this case, we say x majorizes y. A function is called a function on these vectors is called Schur-convex if whenever x majorizes y, then the function on x majorizes the function on y. And similarly, the function is called Schur-concave whenever x majorizes y, then the evaluation of x is less or equal than the evaluation of y. So how do you build Schur-convex functions? Actually, it's quite easy to build them. If you take a real valued function which is convex and consider the addition of the function evaluated on the coordinates of the vector, you obtain a Schur-convex function. And if f is concave, you obtain a surconcave function. So we start with this key lemma number 1. So we have a unicyclic graph with n vertices, and we consider them in the order so that if these are the vertex degrees of these vertices, we obtain an n tuple in decreasing order. Xy is greater or equal than the next one. And since G is a unicyclic graph, it is immediate to check that the addition of the degrees of the vertices is 2n. So we can compare the vectors of the degree vertices of any unicyclic graph via majorization. And in this lemma, we prove that for any unicyclic graph with at least 3 vertices, the vector with the vertex degrees always will majorize this vector, where every degree would be 2, and it's always majorized by this vector. The vertex degree, maximum vertex degree would be n minus 1, then 2 vertices with degree 2, and the rest would have degree 1, would be pendant vertices. So given any function, real function f, we define this addition. This function evaluated on the degrees of the vertices of the graph. This is not any real topological index, but it's a generalization of many of them. Many of degree-based topological indices are defined changing the function here. So, like this, we have a general approach to study this problem. So, this lemma proves that this is a lower bound via majorization. So, if this function is convex, this generalized topological index will be surconvex. So this is going to give the lower bound, and this is going to be the upper bound. So if this f is convex, this would be surconvex, and all twos will be the lower bound. This will be the upper bound. Moreover, these bounds are attained by concrete graphs. This bound is attained by the cycle graph, and this upper bound is attained by this graph, UN3, which I'm going to show you, which is in the next slide. Also, if the function f used here is concave, then the bounds are the other way around. This is now the lower bound, and this is now the upper bound. The extremal graphs are again UN3 and the n cycle. The n cycle is just a cycle where every vertex has degree 2, and UN3 is just a triangle and n minus 3 pendant vertices on one of the vertices. So this has degree n minus 2. These two have degree 2, and all these have degree 1, which is the upper bound, which majorizes here any other sequence. So we have upper and lower bounds for this when f is concave and when f is convex. And this applies to many topological indices. For example, if we consider the variable first Zagreb index, which is defined like this, we mentioned before, this function, t2 alpha, is convex if alpha is in these intervals, and strictly concave if alpha is between 0 and 1. So this is going to be a surconvex function for alpha in these intervals, and surconvex function if alpha is between 0 and 1. And as a corollary of the previous lemma, we obtain a lower bound for an upper bound, a lower bound for the variable first Zagreb index for any unicyclic graph if alpha is in these intervals, and if alpha is between 0 and 1, we obtain that this is now the lower bound and this is now the upper bound. The extremal graphs are again the n cycle UN3. Also, if we go to more particular cases, if alpha equals 2, we obtain the first aggressive index. If alpha equals 1, equals minus 1, it is the inverse index. If alpha equals 3, we obtain the forgotten index. So we have sharp lower and upper bounds for all these indices. Moreover, if we define this generalization of topological indices, where we consider a function on the degrees and the product over all the vertices of the graph. Since the logarithm is strictly increasing, a unicyclic graph is extremal for this generalized index if and only if it is extremal for this generalized index. Thus, we apply lemma 1, key lemma number 1 again for this. And if the logarithm of f is convex, then this is surconvex, and this is the upper bound, and this is the lower bound. And if logarithm of f is concave, then this is now the lower bound, and this is the upper bound. Again, the extremal graphs are, once again, the n cycle and UM3. Thus, we obtain lower and upper bounds for the Naruma-Katayama indices and the extremal graphs. So it works for any topological index which is defined in this way. So we can consider the problem now fixing the maximum degree delta in the graph. And we study it the same way with the same tool, so I'm going to go really fast over this and I'm not going to present all the results. Just give the general idea. So we consider, given any n greater than 3 and the maximum vertex degree between 3 and n minus 1, we consider all the n tuples starting with the maximum degree delta. These are decreasing order, and the total addition is 2a. So this would represent the vertex degrees of any unicyclic graph with maximum vertex degree delta. And we denote like this the lower integral part of t, so which is the greater integer less than or equal to t. So key lemma number 2. Using majorization again, if we have a unicyclic graph with at least 4 vertices, with 3 vertices, the unique unicyclic graph will be the triangle, so the result will be trivial. The maximum degree is at least 3. So we consider this sequence. The first one is delta, then we have twos, and then ones, so that the addition of all is 2n. So this sequence would be majorized by any other possible sequence which is from a unicyclic graph with maximum degree delta. Also, for we have key lemma number 3. We have an unicyclic graph with at least 4 and the maximum degree 3, at least 3, and Q is this number. So we have two different cases depending on this number. If Q is 1 or n equals to delta minus 2, then we have S, this number, and this sequence, delta L's, S2 and 1s, this majorizes any possible sequence. And if Q is greater or equal than 2 and n is not this number, then let R be this number, and the sequence will be delta for the first Q numbers, then R, and then the rest are just ones. So in this case, this sequence will majorize any possible sequence for unicyclic graphs in these conditions. So, like before, we use this general approach. We define a generalized topological index as an addition, as before, as an additional function over the vertex degrees, or as a product of the function of the vertex degrees, and depending on if f is concave or convex, we obtain lower and upper bounds for all the indices we saw before. Again, this sequence, delta, then twos, and then ones, would be the lower bound if the function f is convex. And these, depending on the case, are going to be the upper bound. Are going to define the upper bound if f is convex. The corresponding extremal graphs would be these. The computations are a little bit more complicated, but the ideas are just the same. If the basic function f, the real basic function f is convex, then this is the lower bound and these are the upper bounds. This is just the cycle with k vertices and delta minus 2 paths here attached to one vertex. These have maximum degree delta. Then we have twos and one for each, one pendant vertex for each path. This is just a triangle with delta minus 2 pendant vertices and n minus 1 minus delta pendant vertices. Would be extremal if q is 1 or n is 2 delta minus 2. If q is greater than 2 and n is this number, then the extremal graph would be a cycle with q vertices and delta minus 2 pendant vertices at each one. And finally, if q is greater than 1 and n is greater than this number, the extremal graph is a cycle with q plus 1 vertices, delta minus 2 pendant vertices in each of them except from one, which has these pendant vertices. And that would do it. This is the passive bibliography, and this is the reference of this work. And if you have any questions, I'll be glad to try to answer them. Thank you very much.